well, we see all those different energy levels there based on the calculation. And then here, energy is conserved, remember. So if you have an electron on the ground state, getting it to the first excited energy level, well, it may require you to put in, for each mole of electron there, it may require you to put in 984 kilojoules of energy. If that electron is coming back down to the ground level, same amount of energy has to be released. There's a negative number there. Negative means exothermic. So this is release of energy. When the electron is coming down to a lower level, that's going to be releasing energy there. So based on this, the energy is conserved. Energy is a state function, as we just talked about earlier today. If the electron is coming back from level 3 to level 1, we can separate that step into multiple steps. The electron can go from 3 to 2, then 2 to 1. Okay? The total amount of energy for the electron to go from 3 to 1 is the difference between E3 and E1. If it takes multiple steps, eventually, well, if you add those two numbers together, you still end up with E3 minus E1. Okay, so it doesn't really matter, once again, energy is a state function. It doesn't really matter how you go from point 1 to point 2, or point A to point B. And you may take different paths there, but the thing here is that the total amount of energy is conserved. Now that energy is the energy carried by the radiation. This is the equation that we can use to calculate the energy carried by the radiation. Okay, so if you know the difference between two energy levels, you know that much energy, say the electron is going to be moving from level 2 to level 1. This is the amount of energy that will be released. This energy has a relationship to the frequency. This is how we calculate the frequency. Okay, so Niels Bohr did all the calculation there, and for the three lines that we observed for the hydrogen atom there, and we see the violet and the purple line, we see the bluish green line, and we see the red line there. And it's all a result of electrons coming from a higher energy level, different higher energy level back down to the end of 2. And obviously, why do all those electrons come down to level 2? Well, they can actually go back down to the ground level, but this is the region that we cannot see with our naked eyes there. And when we have to use an instrument there, we can actually observe these ultraviolet region wavelength there. There's also infrared region, there is a wavelength. So this happens to be something that we can see without using any equipment there. Okay. Now all of these, the line emission spectrum can be calculated for the hydrogen atom, can be calculated. So people are really getting excited once Bohr published his paper and said, well, this is what I come up with in the theory. Based on this theory, for hydrogen atom, we can actually determine the origin of the line emission spectrum. Now the success there is that we can work out everything about hydrogen atom there. But the thing is, the problem is there, if you have something with more than one electron, then the calculated value will not match what we observed in the laboratory. So people were getting a little bit overly excited when we tried to, once we understand how to figure out the line emission spectrum for hydrogen atom, then we realized, well, there's 100 other elements that we know of in this world. This theory cannot actually explain. How do we deal with that situation? Each element has a different emission line spectrum. Where do they come from? How do we explain them? Well, that brings up the revolutionary, the quantum revolution, and that is we're talking about the particle wave duality. So that's a prelude of the quantum mechanics there. And Louis de Broglie, in response to Planck-Einstein's assertion, Planck and Einstein's assertion, that light was particle light. He used the term photon. And that stated small particles should also exhibit a characteristic wavelength. Okay, so electromagnetic radiation are no longer, electrons and electromagnetic radiations are no longer just wavelength, no longer just radiations, and no longer just the waves. They're also like particles there. So on the other hand, if you have a tiny particle that moves at say, close to the speed of light, they should also exhibit a characteristic wavelength. Okay, so by combining the Einstein's equation E equals to mc squared, and then h times the frequency equals to mc squared. Now, if you rearrange that equation, combining these two equations together and rearranging the equation there, h times the frequency divided by the velocity equals to m times c. M is the mass, c is the velocity. M times c is mass times velocity, is defined in physics as momentum. So, in substituting the p into the equation there, h over lambda, over the h the Planck constant over the wavelength equals to the momentum, or lambda equals to h over p. So, momentum, by definition, is mass times velocity. So, for any particle, in a sense, you can calculate the wavelength of that particle. Planck's constant divided by the mass times the frequency times the velocity. Now, this is not the frequency. This is the English letter v. Okay, m times v. M times v equals to the momentum. Okay. Now, so light waves actually have mass. That's new at the turn of the 20th century. People never thought about light waves actually have mass. And then particles will have a wavelength. So one of the calculations in your textbook, in the example in the textbook there, and we ask you, if you throw a baseball out, we know the mass of the baseball, we know how fast they're traveling, we can calculate the wavelength from that baseball. Now, that is, well, in a pure mathematical sense, we can do that. But in the macroscopic world, when you have something as big as baseball, they're moving too slow to exhibit that wavelength there. So when you calculate the wavelength there, you can see the wavelength is extremely small. Okay, so this is the equation that you can use to do the calculation. We do have several homework assignments there, questions there, and asking you to do the calculation, giving you the mass of the electron, giving you how fast they're moving. We ask you to calculate the wavelength, and that actually fits into the microscopic world. But if you calculate the wavelength of a moving object that's macroscopic there, like a baseball there, and you will end up with an unreasonably large or small number. And so this equation is pretty much reserved just for the microscopic world. Very tiny particles, like electrons, like the photons. Okay, so in this case, around 1926, the quantum mechanics or wave mechanics developed in 1926 by Erwin Schrödinger, and the equations uses a set of three mathematical equations to describe the energy state of a particular electron. And those electrons, those equations, using those equations, you will be able to calculate where they are, how much energy they possess, and then how fast they're moving. Okay, so this is with the Albert Einstein's publication about the photo effect, the wave and particle duality there, and that is photo effect. What's that term I was thinking there? Photoelectric effect there. Okay, so it's a wave and particle property based on the light, and then the electron wave. Electrons are very tiny particles there, and they can exist